Hello, this is Mrs. James, and we are making our way through our review for our end of course exam, and this is Astronomy Part I. I apologize, I have a cold. I will do the best I can. Alright, we're going to start by talking about your address, and by your address I mean your galactic address. Where are you right now? You are in room 311, which is in the 300 hallway of Watkins Memorial High School, which is on Watkins Road in Pataskala, which is in Ohio. We're going to keep going, telescoping out, which is in the United States, which is in North America, which is on Earth. Earth is in the solar system. The solar system contains one star, which we call the Sun, 8 planets, and lots of what I would refer to as space junk. Some of that's called asteroids, some of it's called comets, some of it's called dwarf planets, and some of it is called other things. Now, the solar system is in the Milky Way galaxy. The Milky Way galaxy has many, many stars in it. It has 4 arms in a spiral pattern. We are in the arm that's called the major spiral arm, and we're about 3/4 of the way out on the arm. So we're closer to the end of the arm than we are to the center of the solar system, of the galaxy. The Milky Way galaxy contains billions of stars. Many of them are quite a bit like our sun. It has an unknown number of planets, probably many, many of them. Many stars probably have multiple planets, and astronomers believe that it has a black hole at its center. And it's pretty big. It would take light, not people in a spaceship, but light, 100,000 years to travel across the galaxy. Now, there are many, 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 many galaxies. There is a group of galaxies that are clustered together, and we are in that group, and it's called the local group. There are other groups, and they have other names. And then that cluster of galaxies that we call the local group is one of many clusters that are in the universe. So the universe is everything, and it contains billions of galaxies. It's important for you to keep straight the difference between a solar system, a galaxy, and the universe. So where do scientists get their ideas about the universe? It would take us, now I'm not talking about light, now I'm talking about us. It would take us in the fastest spaceships that we have about 200,000 years for us to travel even to the closest planet. I'm sorry, I should say the closest sun there, so let's correct this word. So please correct that in your notes. To get to the closest sun. It wouldn't take us nearly that long to get to the closest planet, which is Venus. So get to the closest sun. Let's try it one more time. Get to the closest star. Alright. Now, technology provides the basis for many of the new discoveries that are related to space and the universe. So we clearly can't go to other stars because they're so far away, but technology can bring information about them to us. We already learned about the electromagnetic spectrum. So remember that all those different kinds of waves are coming to us from those different stars. So those stars are sending us visible light and ultraviolet and infrared and radio waves, etc. You are familiar with telescopes that see visual light, but there's also telescopes that collect radio waves and X-ray and radiation, and all across the electromagnetic spectrum. There's computers that are used to manage that data. There's space probes out there in our solar system that are gathering data and materials. The Hubble telescope is taking pictures up from orbit. So we even have things here on Earth. We have the accelerators, the super colliders, that do experiments, and they can provide subatomic particle energies that simulate the conditions in the stars and in the early history of the universe. So in other words, we can try to create, using the super colliders, the accelerators, we can try to create a condition similar to the beginnings of the universe or the beginnings of stars. So, summarize, even though we can't go to the other stars, we can gather lots and lots of information about them. Let's focus on one important example, the Doppler effect. Remember the Doppler effect? We learned about it in our waves section. So let's go ahead a page quickly. Here's a picture of the Doppler effect. Remember, if we have an object that's moving while it emits waves, the waves in front of it are getting squished together, which means they have a shorter wavelength and a high frequency. The wavelengths behind them are getting stretched out, which means that they have a higher wavelength and a lower frequency. And when we learned about this with sound, we talked about how this would make the sound of, say, a race car going past you go as it went past. Well, the same thing happens with light. So, when we look at the stars and the galaxies and the other things in the universe, what we see is redshift. Alright? Redshift is this part of the waves during the Doppler effect. What that means is that these stars and galaxies are moving away from us. So we're seeing them from this point of view. Now, they're not just moving away from us, they're moving away from each other. They're moving away from everything. So while we might find an occasional thing moving towards another thing, in general, everything in the universe is moving away from everything else in the universe. We can use computers to trace their paths back to a central location. Again, the central location is not Earth. This was the big discovery that led to the formation of the Big Bang Theory. Alright, let's talk a little bit more about redshift. Stars have different elements inside them. Similar, but slightly different. When these different elements burn, they emit different colors of visible light. Now, those are combined in one light, but astronomers can separate that light coming from a star into its component colors, just like a water droplet or a prism can break down light into a rainbow. So right here, I want you to see that right here we have what we call a spectrum, and this is the light that's coming from a star. Now, you might see that there's little lines coming through here, alright? These little lines here, and here, and here, and here, and here, that's the actual data. That's what tells astronomers what chemicals are inside that star. In particular, bands showing up on this spectrum are indicators that a certain chemical is burning. Alright? So, in other words, if there's hydrogen in the stars, we know that certain of these lines will show up. If there's helium in the stars, we know that other lines will show up. Now, this is the spectrum that would be coming to us from a star that's moving away from us. You can see how this line has been shifted this way. This line has been shifted this way. Everything is being shifted towards here, and this is the red end of the spectrum. That's why it's called redshift. In other words, these waves are shifted towards the red end of the spectrum. These waves are shifted towards the blue end of the spectrum. We see redshift when we look at stars. That's what tells us that we're seeing this end of the spectrum. So, scientists can take the light that's coming from a star, they can use equipment to break it down into the spectrum, they can look and see if redshift is happening, and then they know that that star is moving away from us. So let's look at a series of redshifts. Alright, we have a simpler spectrum here, it's only showing us a few of these lines, so this star would have fewer chemicals inside it. It's not that each of these lines represents one element, the patterns represent it. This is a laboratory reference, so this would be if a star was not moving away from us or towards us. A star that's close has got a little bit of redshift. You see how these lines are shifted a little bit to the red? They're shifted about that far. Well, now we have a nearby galaxy, so it's going to be farther away, because a nearby star would be in our galaxy, and a nearby galaxy would be in a different galaxy, so farther away. And look, the redshift is farther away, so those waves are shifted farther towards the red end. Okay? And a distant galaxy, look how far the redshift is. Alright, and now you look here, these two bands right here have been shifted all the way over to here for a very distant galaxy. So we can see that the redshift is greater for things that are even farther away. Redshift is smaller for things that are close. The Doppler effect, this idea of redshift, allows us to determine what the relative velocities are of those other galaxies. So the greater the redshift, the greater the relative velocity compared to us. All right, so this is moving away from us faster than this is. This is moving faster away from us than this is. This is moving faster away from us from this is, and so on. All right, the Hubble's law was written by a man named Hubble. He was the one who came up with that law, and it says that the relative velocity is proportional to the distance a galaxy is from Earth. So again, the farther away the galaxy is, the greater its relative velocity. So the faster away it's moving compared to us. We've been able to take that information in this law, and we've been able to figure out just how fast the universe is expanding as all these different celestial objects move away from each other. So here's a picture of Hubble, and here's a picture of the Hubble telescope, which is not related directly to Hubble's law, but was named in honor of him, and it's a permanent telescope in orbit around the Earth.